Today, we're going to make you a physicist in forces. We're going to start out by describing what mass is. Now this dime has 1 gram of mass. You're probably wondering what is mass and what is a gram, but that's what I'm going to teach you. Is it easier or harder to make 1 dime speed up or this stack of dimes speed up? You're right. 1 dime is easier to make speed up, as you can see here. This is because the less mass an object has, the easier it is to make it speed up or slow down. The more mass an object has, the harder it is to make it speed up or slow down.
Hi, Duffy.
Mass is measured in a unit kilograms. 1 kilogram is equal to 1,000 grams, or 1,000 dimes. 1 kilogram would be about the size of a pineapple. Now that you have learned what mass is, we're going to move on to force.
You're probably wondering what force is, and also what caused the dimes to speed up. Force is what caused the dimes to speed up. Force is the push or the pull that causes an object to speed up, slow down, or change direction. When I push the dimes to the right, the dimes move in the same direction as my force. Now that you know what force is, it's time to move on to acceleration. What happens when you apply a force to an object?
Acceleration is when an object speeds up, slows down, or changes direction as a result of the force. When I apply a force to these dimes, they go from sitting still to moving. Their speed increases from 0 to an amount, which is called acceleration as a result of the force. Acceleration can also happen when the dimes go from speeding up to slowing down. A third example of acceleration would be if the dimes were going one direction and then changed direction. That's also an acceleration.
Now we're going to talk about equilibrium. What does that mean? Well, it kind of sounds like equal, which is the state of the forces on the object. So first, we have force 1, and it's pointing to the right, and its magnitude, or how big or small the force is 2 newtons. And this is our object. On the other side of our object, we have another force acting on it. And it's the exact same strength as the first force acting in the opposite direction, making it negative 2 newtons. When you add these two forces up, the total force is 0, because 2 minus 2 is 0. So, equilibrium is the state of an object in which all of the forces acting on it cancel each other out to be 0. There are 2 types of equilibrium. The first type is static equilibrium. This happens when all of the forces acting on an object add up to be 0. Like these dimes. There's no force that's pushing an object in a certain direction without another force that adds up to cancel out on it, so these dimes stay at rest. The second type of equilibrium is called kinetic equilibrium. This happens when an object is traveling at a constant velocity, or constant speed. It's not speeding up, or slowing down, or changing direction. All of the forces adding up onto this object that is in motion are 0. Like this stack of dimes. It's speeding up, but now it's traveling at a constant speed. It's not speeding up, or slowing down, or changing direction, which means that it's in a state of kinetic equilibrium.
Equilibrium helps to explain Sir Isaac Newton, the famous physicist, first law, which states that when no outside forces act on an object, the object will stay at rest or move at a constant velocity. For example, when no forces act on these dimes, they stay at rest. Or when 2 forces of equal and opposite measurement act on the dimes, they move at a constant velocity and do not accelerate.
2, 3. Sir Isaac Newton also had a second law that said that the acceleration, or the speed up, slow down, or change in direction, is equal to the force applied on the dimes over the stuff in the dimes that made it hard for them to move. So, if I was to apply a force of 2 newtons, remember, we named the measurement of force after Sir Isaac Newton, of 2 newtons to these 10 dimes, and these dimes each had a mass of 1 gram, as we said earlier, their total mass is going to be 10 grams. So, with a force of 2 over a mass of 10, the acceleration is going to be equal to 1/5.
So this really smart physicist, Sir Isaac Newton, also proved a third law. His third law states that all forces come in pairs. So, for every force, there's an equal and opposite force. So, when I push down on this table, the table is also pushing back up on me, which is why I don't fall through the table.
Now I'm going to teach you about one of our 4 special forces, weight. You may be thinking, weight isn't special, it's ordinary. I go to the doctor every year and stand on a scale and they measure my weight. But in reality, you probably don't even know what weight is. Weight is the force of the center of the earth pulling objects on the surface of the earth towards the center. No matter where a person stands on earth, they are being pulled towards the center. Let's go back to Newton's second law. This states that acceleration equals force over mass. This law can be rewritten as force equals mass times acceleration. The acceleration in which you are being pulled towards the center of the earth is a constant of 10. That times the mass, remember mass is, for example, a dime is 1 gram of mass. So for your body, think of how many dimes would take up to make your body. So mass times acceleration, the constant of 10, equals the force due to gravity. The force due to gravity, again, is the force of the earth pulling any object on its surface to the center. The force due to gravity is also called weight, which is special because it always acts towards the center of the earth.
Remember before when we pushed on the table and we said the table was pushing back on us and that's the reason we didn't fall through the ground? Well, it turns out that force that's pushing back on us has a special name. It's known as normal force or a support force. So when I push on the table, the support force or the normal force is pushing back on us. The normal force always acts at a right angle to the surface of the object. So you see how the table goes this way? The normal force is acting up, right out at a right angle to the object. Before, when we said that the center of the earth was pulling us towards it, the reason that we don't fall all the way into the middle of the earth is because there's a normal force or a support force acting on us to keep us from falling there. That support force is the Earth's crust.
Another one of our special forces is friction. Friction is the force that opposes motion. So, if I push this stack of dimes this way, friction is the force that's going to try to block them from moving and act this way. A smooth surface, like this table or an ice rink, has very little friction because it's really smooth, so there's not a lot of stuff coming up out of the surface to try to block the motion of an object. However, if we have something like Legos, they have a lot of rough stuff up on the top of them. And this rough stuff up coming out at the top is going to try to block the motion of an object. So, if we have some Legos traveling this way, friction is going to try to push them back this way and make it slower for the objects to move. Friction is special because it always acts in the direction opposite of the direction that the object in motion is moving. Remember when we talked about equilibrium and how there's 2 types of equilibrium? How there's static equilibrium and kinetic equilibrium? Well, there's also 2 types of friction, static friction and kinetic friction. You know how when you're trying to push a table and how it's always harder to get it to start moving, but then when you actually start pushing it, it's a little bit easier? Well, that's an example of the difference between static friction and kinetic friction. The friction opposing the motion of an object when it is starting to move is always greater than the friction opposing the object once it is moving. Static friction is the friction that opposes the motion of an object once it starts moving. So, if I try to push a table this way to get it started moving, the static friction is going to push this way and try to get the object not to move. And then also, the kinetic friction is once the table's already moving, that's the friction that opposes the motion of the object. So, right now, the static friction is pushing this way, but now, kinetic friction is pushing that way. There's two different types. And static friction is always greater than kinetic friction. Go.
Now let me introduce you to my friend mu. Even though that sounds like something a cow would make, it's really an ancient Greek letter that symbolizes how much friction there is. Remember before when we were pushing the table and how we said there was more friction, more static friction to get the table going, and then there was less friction once you already had the table moving? The mu was greater to get the table going and was less once the table was already moving. A smooth surface, like this table's, going to have a smaller mu, while a rough surface, like the top of the Lego, is going to have a bigger mu. Remember earlier when we learned about weight, which is the force that draws an object to the center of the earth? Well, look at this ornament. This ornament is being drawn towards the center of the earth because it has mass, so it has weight. However, this object isn't falling to the center of the earth. Why is that, you may ask? We know it doesn't have a support force because there's nothing underneath it supporting the object. So there must be a completely different force acting on the ornament. There is, and this force is called tension. It's the force of these ribbons holding the object up to keep it from falling. The tension, or the force on the ribbons, is acting opposite to the force of gravity, or the weight, which pulls the object downwards. If we were to cut the ribbons, the object would fall. So we know that the tension is acting upwards. Tension always acts in the direction that a rope, chain, or in this case, ribbons, is pulling an object.
Now that you've learned all about mass, acceleration, force, equilibrium, Newton's 3 laws, and our 4 special forces, I say we should start calling you Sir Isaac Newton.